Hey, it's Tuesday, March 5th, about 10 minutes to 7. Skies will be chancy tonight. I'm seeing Sirius, Rigel, Betelgeuse, and clouds. Not sure if you can see it. We've got the camera set up for the display screen. There's a good chance I'm going to get through a list of about 12 galaxies tonight. That will be a Mathematica Galactica because it's not part of the series, and I still want to explore this notion of what I call spatio-temporal moments. Ooh, I almost slipped because we've had snow today and we've got ice. So, good thing I used to ice skate as a kid. Anyway, so I've got the scope set up. It's parked, of course. But what I'm going to do tonight is I want to show you that I could actually resolve Rigel's companion. Now I don't have any data on it. Looked like it was about 5 arc seconds separated, maybe magnitude 8, 7 or 8. We're going to have to play with settings in order to do that. Here's the screen now. We're not looking at anything in particular, but that's the current setting. And before the sky started getting dark, I was able to resolve Rigel's probably 6th or 7th magnitude companion. Let's move on and set the camera up and then take a look. I also want to take a look at Betelgeuse because they mark the bookends of stellar evolution in terms of supermassive stars. One's at the Rigel, a 20-mass stars at the beginning of its evolutionary process, and the other, Betelgeuse, is about half that, having lost half of its mass through irradiation and ionization of the photosphere. So let's have a look at those two as we get started here. Okay, what we have here is a view of Rigel, and I had focused it beautifully when I went in. Now either we're out of focus again, earlier this evening when I came out to check things out and noticed that we've seen Rigel's companion. And let's see. Okay, well, it's a little bit off, but we're not seeing the companion now. Let me lock down the focuser. I almost hate doing the locking down of the focuser because it can disturb the scope in and of itself. It is nice that there is a focus lock on this scope, however. All right, that's about as tight as we're going to get. And, oh, we got clouds. All right. Let's see if we can resolve that companion. Now, the disk, best resolution generally of anything is just as you're heading towards the evening. After the sun sets, as the sky's still a little bit blue, that's when you get your best views of planets and stars, etc. They're very sharp. That happens also at the eyepiece, by the way. I am faintly seeing a star here. Let's push it up just a little, and we're starting to swell. Overwhelmed. Okay, so I did manage to actually see Rigel's companion earlier. Okay, well, let's not spend any more time looking for that. But let's say, as I mentioned in Mathematica Galactica 4, where I introduced the idea of spatio-temporal moments actually pervading the cosmos, and then when you have a Big Bang event, all you're really doing is liberating massive amounts of pure energy, which causes these temporal moments, according to stressor theory, to basically entangle themselves in all kinds of phantasmic subatomic particles, most of which have very short-lived lives, but some of which actually have an enduring capacity to maintain their particle nature. Many of them probably pass through what is known as the quark stage, and then the certain quarks just are not sustainable, cannot be built with other, matched with other quarks to create subatomic nuclear particles. But by randomly cramming all of these, what I call spring theories, not springs, together, some of them are sustainable, become matter. And the reason why these spatio-temporal moments do this is they just don't like being subjected to the immense amount of energy that is released. At the time of the Big Bang. Later on, of course, it's not as much of an issue. You basically have your standard photonic energy levels that pass through them. They act like springs, they work together, create sinusoidal waves of different frequencies, they rebound nicely, but they are dealing with stress, but it's stress they can handle. It's only under super stressful situations where massive amounts of energy are liberated and that they end up co-entangling and creating sustainable particles with long enduring half-lives. And so that was the basic thesis that came out of Mathematica Galactica 4, where we talked about the recessional velocity and the fact that the speed of light may not be consistent throughout the cosmos. Okay, now we're on to Betelgeuse. Betelgeuse was the very first star that was actually resolved through telescopy, so they could actually get an estimate of its size. And apparently it's so large as a red giant who is swollen due to the fact that its nuclear core is now irradiating with so much pressure that it basically pushes the photosphere out. I believe the data I've heard about, at least the anecdotal information, probably out to the asteroid belt of our own solar system, which means extending out as much as 350 to 400 million miles in diameter. Now, Betelgeuse is at the end of its stellar evolutionary process. Both Rigel and Betelgeuse are off what is known as the main sequence. In other words, neither of these stars has achieved the kind of basic sustainability that makes them be consistent in their behaviors. Rigel and Betelgeuse both are variable, although Betelgeuse is a bit more variable than Rigel. And the reason I bring this up is because, once again, I mentioned this in Mathematica Galactica, that they're like, and I'm iterating it now, they're like bookends of stars that are at the beginning of the process and at the end of the process of stellar evolution. They just both happen to be supermassive stars. They were both what I would call progenitor stars that helped set off the kinds of shock waves in the cold dark matter that resulted in many other stars forming. Now, there's no cluster associated with either of these stars, although Rigel may have 4 companions, possibly 3 at least, but possibly 4 companions. All of those companions are in the main sequence, which means they're going to exist, they're going to last for a while. The other astonishing fact that came out of the research was that red dwarf stars with masses 1/10 to 1/20th of the Sun potentially have a longevity in the trillions of years, whereas our own sun, of one solar mass, of course, has about a 10 billion year lifetime before it'll turn into a planetary nebula and begin to throw off highly ionized particles into space as its core heats up, just in the way that Rigel and Betelgeuse's cores are very hot now. Okay, now I'm going to step through the exposure time settings. Notice the shutter speed's now 120th of a second. The eye operates at about 1/30th of a second, collecting photons. And the gain is 42. I don't think that the CCD imager has anywhere near the sensitivity the eye has. But anyway, let's go ahead and step through this now and watch as something emerges. 50th of a second. 2 flood is about 1/25th of a second, which is roughly the about the exposure time of the human eye. 4 flood, you double that. Now we're up to 8, 16, 32 flood. We're really pushing it now. 32 flood is probably somewhere in the range of a 10 to 12 inch scope. 64 flood. 128, I figure, is probably somewhere around 18 to 20 inch scope, and our nebulosity is beginning to reveal itself. And I'm going to center on this particular nebulosity, which is Messier 43. Now notice right where this bright central region was, I'll back it off a little bit, there was a star that revealed itself. That star, let's go down, come on. It's going to take a while. That star that was positioned right there is probably the progenitor star. It's a somewhat massive star, probably not as massive as Rigel, but basically this is the star that is setting off the emissive characteristics of Messier 43, where other stars, due to shock waves, will begin to form as a result of first passing through the phase of a Bach body. An astronomer who was investigating this, I believe in the 1930s or something, and more data has to be forthcoming. Anyway, so now as we continue gathering photons, we are basically beginning to reveal the nebulosity itself, which has an average surface brightness of about 14, I think I calculated mentally last time, but you have to keep in mind at 150x, which we're operating at, that's really more like an average surface brightness of 15.5. And I'll have more to say about average surface brightness later, because some very intriguing data is available to you on the Sky Live that has to do with average surface brightness based on arc seconds, magnitude instead of roundish arc minutes, it is roundish arc seconds, which becomes a factor when you have an imager working through a telescope that's capable of resolving down to a pixel of 1, maybe 1.2 arc seconds, which is one of the reasons why we do not get as deep a look at galaxies as we might expect. Give me a moment here, I'll center up Messier 43. Okay, I'll give you that data on Messier 43 as you have a look at the, remember it's going to take 50 to 60 seconds to fully integrate an image using 256 flood. And the reason I'm using 256 flood is because we're going to be operating once again at 150x, which really thins out the light. And we're getting basically at we're basically getting the views of 64 flood that we would do in terms of light collection at 150x. Let's see, 64 to 128 to 2, yeah. So I'll have to think this through in a little bit, but there's our view of the Conch Shell Nebula, Messier 43, an emissive nebula in Orion, star-forming region, magnitude 7.020 by 15 arc minutes. So that means 300, average surface brightness of 300, 100 is 5 magnitudes, 250 would probably be 6 magnitudes. So let's assume this is about a magnitude 13.5 average surface brightness. And we're getting a pretty decent view, despite the fact that we do have some high thin clouds that are drifting over on occasion. Now let's go on to our galactic studies of this evening. All right, we're directing the scope to NGC 2207, a galaxy in Canis Majoris, the big dog. This is an excellent galaxy, and I recommend you get a look at it if you can by going online and searching on it. It's magnitude 10.8, largish, 4.2 by 2.6 arc minutes, spiral with a bar, the lowercase bc, and a ring. And as mentioned previously, if we were operating at 75x, we would probably be able to vision the ring, see it on the screen, since rings tend to be about 4.5 magnitudes fainter than the collective magnitude of a galaxy, which would be 15.3, but at 150x, we're pushing it. All right. Anyway, this particular galaxy is also low in the sky, which precludes being able to gather enough photons for that. It's at minus 21 and almost a half degrees. We're at right ascension hour 6, 16 minutes and 21 seconds. I do believe the galaxy is visible right there on the screen. So after centering on Messier 43, we seem to be doing a pretty good job of go-toing anything in the southern sky. This particular galaxy is probably about an hour from culmination, but the scope has not decided it wanted to do a equatorial flip to look east. We are basically looking west with NGC 2207, even though it has another hour before it'll achieve culminate. And sky dark is probably within another 15 minutes to a half an hour. But this is a baseline view since we imaged this very same galaxy as part of the Mathematica Galactica 4 series, which featured discussions having to do with recessional velocities. Our next galaxy is NGC 2211, another galaxy in Canis Majoris, the big dog. Magnitude 12.7, perfect oblately presented 1.4 by 0.7 arc-minute spiral with a bar and lenticular. So this is a galaxy that is either collapsing towards pure lenticular status or is expanding in some way, having assimilated more cold dark matter in another galaxy. Now I can't tell you whether the galaxy is present on the screen. I'm in a very bad observing position. I'm hoping it'll be somewhere just about up here where NGC 2207 was located. We shouldn't be too far from it. We went a little bit north. We went up about 4 degrees, minus 1832 at this point, which typically means studies begin to gravitate in this direction. And there, I believe, is the core of our galaxy. So we do have to remember at 256 flood to give things at least about a minute to fully form on the screen, especially given the fact of something else that was very interesting to me that I've been studying. And that is average surface brightness on the basis of 1 arc second rather than 1 arc minute. So 1/360th of an arc minute. NGC 2207, and I only have a few of them here. The last galaxy we looked at was probably one of the faintest galaxies in terms of magnitude based on arc seconds, average surface brightness. It was magnitude 23.84. Now I didn't write down these other ones, so they're going to be in the range of 23.84, which was the faintest average surface brightness in arc seconds, to 22.86. So the range basically is 1 magnitude, which means the brightest ones are 2.5 times brighter. That would be NGC 2227 we're going to look at. And the faintest of the evening is 2207. 1 magnitude difference between them, 2.5 times brighter or fainter, depending upon which way you want to go. And then we just gave NGC 2211 quite an opportunity to show strutted stuff. Let's move on. As it turned out, NGC 2212 was not even, I didn't even hear a click of the stepper motor. Another galaxy in Canis Majoris, fainter though, magnitude 13.54. 1.5 by 0.8, almost obliquely presented, which is probably the average presentation of galaxies that you would see in a telescope. It's a spiral with a bar and a lenticular, so it's halfway between a lenticular and a lowercase a. So we'll call it a z plus a half. 90 million light years distant, and we're at minus 18.5 degrees. That 90 million light years distant basically says that it's got a recessional velocity somewhere, I believe, around 2,000 kilometers per second. Now, it is getting down in the zone where peculiarities that have to do with distances and our own galaxy's motion and our own Earth's motion, etc., around the sun and the sun around the galaxy, astronomers are pretty much able to wash out our solar system's motion and the motion of the Earth in terms of calculating these recessional velocities and based on redshift. So once you get under 100,000 light years, you've got a possibility of somewhere between a 10 and a 20% error based on the peculiarities of motions in our region of the universe. So anyway, that is something you want to keep in mind. I do believe our galaxy is here. I see another one there, and I see another one there. The stars are looking pretty well focused. It's possible that it got messed up again. I might play with it again later on. But we are looking towards NGC 2212, and we have to figure out pretty much on our own which of those faint fuzzy blotches is our galaxy in Canis Majoris. Our next study is NGC 2216, another galaxy in Canis Majoris. Magnitude 12.8, but more football shape, 1.4 by 1.1 arc minute. Spiral with a bar in lowercase ab, which means between A and B, which is 1.5 times removed in the spiral direction from lenticular class Z's, as I call them, Z equals 0. This galaxy is 131 million light years distant. We're at minus 22 degrees. So its recessional velocity is probably somewhere around 2,500 kilometers per second. One thing I want you to pay attention to that I addressed a little bit in Mathematica Galactica 4 was the fact that the velocity of light, even measured on Earth, has a certain amount of variability. And so what they do every year is they run measurements maybe 10 times a year, they average them out, and then they just say, well, the meter is 1/300 millionth of the speed of light in terms of wavelength. Now I have to think it through again. I'm not thinking in those terms, but basically the speed of light is 300,000 kilometers per second. That's 300 million meters per second. So they just basically play with the data and they average it out. It's kind of like setting clocks. You know, clocks aren't perfectly matched. The calendar isn't perfectly matched. So they basically go and do an approximation and set the standard for the next year. Anyway, we're looking at 2216 galaxy Canis Majoris, and we're going to move on to our next study of the evening. Okay, we're now off to NGC 2217, another galaxy in Canis Majoris. Bright? Wow, didn't we already do this? It looks like a deja vu to me. Magnitude 10.7, 4.7 by 4.3 arc minutes spiral with a bar and a lenticular class A with a ring 70 million light years distant. No, maybe we didn't see this one. Since it's a lenticular A, that means it's half removed from Z equals 0 or Z. Fairly large, which means 5 by 4 is 20, and that's basically 3 magnitudes, I think. So the average surface brightness is somewhere around 14. We're at minus 27 degrees in declination, but we're not getting a bad view. There's the galaxy, in my estimation, right there, and it's almost a virtually face-on lenticular spiral. That's what we might expect to see. So there's a good view of NGC 2217. I do not have the data on its average surface brightness in arc seconds. It's somewhere in the range of 2384, which was 2207, and 2227, which is 22.86 magnitude. Now the thing that scares me about that magnitudinal, this scope is only really capable of reaching a magnitude 15. So the core, and I have to sit down and figure this out, think it through. The core single arc second of the core certainly has to be brighter than magnitude 15. But we're seeing quite an extension, so this is something I'll be playing with in the next Mathematica Galactica, which has to do with the data available about the average surface brightness in arc seconds and what any single pixel, which we'll assume is about 1 arc second on the screen at 150x, what that really means about the brightness of that pixel. So that's going to be an interesting exploration in our Mathematica Galactica series. Our next study is NGC 2223, galaxy in Canis Majoris. Once again, brightish, magnitude 11.6. There have been an awful lot of interesting galaxies in Canis Majoris. It's 3 by 2.6 arc minutes, spiral with a bar and a lowercase ab, and if you remember, an A is 1 time removed from a lenticular, B is 2, so it's 1.5 times removed. This particular galaxy, 2223, is 123 million light years distant and is at almost minus 23 degrees. The sky looks really nice up there, but I can't really make out the galaxy on the screen. I hope we haven't drifted. Oh, I think it's right there. Remember, it takes a while for these things to formulate when you're operating at 256 flood. And I'll allow it to continue to assemble itself on the screen as we prepare to look at the brightest average surface brightness galaxy on the list tonight, NGC 2227, 1 magnitude roughly brighter than the faintest, which was 2207, which kicked off our series, which means it's each pixel, arc second pixel, because I believe we're resolving down to about 1 arc second at this point, is 1 magnitude brighter than that original galaxy, NGC 2207. So we're going to 2207, 2227, and out. Presumably, we're going to get a view of NGC 2227, and I think it's slowly assembling its photonage right there. Galaxy in, excuse me, Canis Majoris, magnitude 12.5, 2.1 by 1.2 arc minutes. So basically a little more than an oblately presented spiral with a bar and a lowercase c. This galaxy is thrice removed from a lenticular Z, 103 million light years distant, which means what? It means that its recessional velocity is basically right around 2,000 kilometers per second, which equates to a redshift of 2/3 of 1%. Now, one of the things that just astonished me, and I didn't really give this much thought, I kind of probed at it with my imagination a little bit, but the James Webb Space Telescope is now seeing galaxies that have a 13 octave shift, which means 100% 13 times over. Now, basically, what's happening is those color bars on the spectrum of these galaxies, almost 13 plus billion light years distant, basically it's dropping its light and then moving 13 times faster than the light from us. Well, we're actually moving it 6.5 times, half split the difference, but that's an extraordinary thing to think about. It's almost like a boat. Let's say a plane is causing a sonic boom, which I think is pretty close to a half an octave or an octave in terms of sound, and then moves off at 13 times the speed of sound as it moves forward. So it's basically dropping a boom of some kind of sound and is 13 times more distant than speed of sound, which is roughly about 1,000 miles. I believe it's about 700 miles an hour, the speed of sound. So anyway, it just astonished me to think that there were actually galaxies, and the estimated speed of light when it does this at that part of the universe is somewhere around 600,000, 2 times the speed of light as we're now measuring it. But it all gets very confusing, and it really requires a lot of investigation to make sense out of it. Anyway, that little explanation went along with a view of NGC 2227, our brightest average surface brightness galaxy of the evening. Okay, because I'm a little confused about where galaxies are ending up, I went back to Messier 43. And you can see its progenitor star right there. Originally it was about right there, so things aren't tracking perfectly well this evening. I don't think it's very cold out. I'm not sure if it's having much of an effect, but I wanted to go back to Messier 43 so we could get a better idea where galaxies are appearing. I'm going to do another quick synchronization to it, and then we'll go back to continue with our studies of the galaxies of the evening. All right, I've synchronized around the central star of Messier 43, and that's where we hope to see things. Remember, they're going to drift a little bit up this way when we go south and down that way when we go north. Let's move on and resume our studies of our galactic friends of the evening. Because NGC 2227 was kind of central to our discussion of average surface brightness in terms of roundish arc second, I've decided to return to that particular galaxy in hopes that it'll turn up somewhere in this region here. It's very hard to tell. There are artifacts on the screen. This line of artifacts is always present. There's usually one towards the center and several distributed. These are all pixels that are misfiring. If I had to say the galaxy so far, from what I can tell, it's probably right about there, because that was not present earlier. Well, anyway, I can't be absolutely sure about it. So let's go ahead as I dial up the next galaxy. Once again, the data on NGC 2227, galaxy in Canis Majoris, magnitude 12.5, 2.1 by 1.2 arc minute. It's probably somewhere around magnitude 13.5 or 14 in terms of average surface brightness. from the point of view of arc minutes, but in terms of arc seconds, it's 22.86. We're at minus 22 degrees in declination, and I'm going to go ahead while it continues to assemble to dial in our next galaxy, which will be 2263. A lot of skippage here going between these two open clusters. Nebulosity. Nebula, a lot of these are in, some are in Auriga. 2243 is an open cluster in Canis Majoris. Let's take a look at that just to get a sense of what it looks like. It's fairly small, 5 arc minutes. This should be fun. Well, this particular open cluster, NGC 2243 in Canis Majoris, is magnitude 9.4, so fairly faint, 100 stars, so it's quite dense. Brightest of which are magnitude 11.8. It's a class Roman numeral 1, 2. 1 means that most of the stars are roughly the same brightness, I believe, and 2 means it's moderately distributed. Distant, 14,500 light years. We're at minus 31 degrees, so we've gone about pretty far on this one. I do believe the open cluster is right there on the screen. Looks a little nebulous to me, but we haven't gone very deeply south. I appreciate where it's located if that is, in fact, NGC 2243, open cluster in Canis Majoris. Our next study is NGC 2263, another galaxy in Canis Majoris. Brightish, magnitude 12.1, football shape 2.7 by 1.6 arc minute, spiral with a bar and a lowercase ab and a ring. 122 million light years distant. From my point of view, a ring suggests that the galaxy is spinning fairly rapidly. I haven't researched this at all, it's just something that might be of interest to look into. We're at minus almost 25 degrees in declination. The galaxy is anywhere on the screen. I really can't tell, but maybe right about there. I'm off angle, so that could be it. It's not very large. I don't know if it's showing a ring. I wouldn't expect so, because the ring would probably be somewhere around magnitude 17, especially at 100. At this magnification it would be faded out quite extensively. Anyway, 2263. I'm going to go ahead and dial up the next one as it continues to form on the screen. Remember, it needs about a minute. Our next study will be NGC 2267. Okay, one of the reasons we're not getting the views we might expect is the sky looks really black, but it is far south. We're at minus 32.5 degrees. We could easily lose 3 magnitudes right off the top, just because we're looking through so much atmosphere. But it's such a lull out there. It looks so nice and dark to my eyes, although they're not perfectly dark adapted because I'm looking at screens. Anyway, NGC 2267 galaxy in very southern Canis Majoris. It's a fairly vertical constellation. Magnitude 12.2, 1.7 by 1.3 arc minute, spiral with a bar and lenticular, 69 million light years distant, and that value is significant because now redshift and recessional velocities become fairly difficult and challenging when you're that close. So the error could be as much as 20%, and at 70 million light years distant, which is very intriguing because later we'll get the Gamma Virgo group of galaxies, and they're about 60 million light years distant, and there's an awful lot of gravitational welling going on. That welling, of course, I explained with using the billiard table model in the last video, which gives you an idea of gravity wells as being these pocketed regions in a very gauzy pool table without a backing board, which causes the balls to sink down a little bit and attract one another. And it gets very complicated when there's lots and lots of balls on such a table. But there's our view of NGC 2267 such as it is. Okay, just eyeballing it here, we're probably about 3 or 4 degrees south of Sirius in the sky. We're not culminating yet on the central meridian, so we're still looking pretty far south. For a galaxy NGC 2271 in Canis Majoris, magnitude 12.2, 2.1 by 1.4 arc minutes, so it's above the oblate presentation aspect ratio. Spiral with a bar and lenticular. We've seen a lot of those tonight. 110 million light years distant, which means we're about, once again, 2/3 of 1% in terms of red shift, in terms of the first octave of red shift, and we've got a recessional velocity of about 200, let's call it 2,200 kilometers per second relative to our own galaxy. We're at minus 23.5 degrees in declination, right ascension 6 hours 42 minutes. Let this galaxy continue to assemble itself. The next galaxy is pretty neighborly, at least numerically, 2272. And it'll be further south. I got 2 bars left on the camera on this very cold night here in Grant County, Eastern Oregon. Our next study is even further south. We're probably about 6 or 7 degrees south of Sirius at this point, the Dog Star, which the Dogon people worshipped to some degree, iconified, and they said that it had a white dwarf, a small, faint neighbor, which is about the magnitude 8, but it's pretty close to Sirius, and therefore astronomers didn't actually observe it until the latter half of the 1800s. Very intriguing. NGC 2272 is a galaxy in Canis Majoris, magnitude 11.7, 2.4 by 1.6 arc minute, nearly oblately presented spiral of the lenticular class. No bar this night, so there's no drinks being served up at NGC 2272. 88 million light years distant. We're at minus 27 and almost a half degrees in declination, and our next galaxy will be the final one of the evening. Ooh, they're all in links. Oh, there's one in Gemini, 2274, which is going to be pretty high up. Hopefully we don't get blocked by the roof try. All right, we're not going to see anything of this galaxy. The clouds are now rolling in, and we're looking through the thickest part of it. I will make sure I try to capture this one next night out. And the weather is supposed to improve around here. But let me tell you about NGC 2274. So we'll anticipate it in the future. And the clouds have now rolled in over the region of Canis Majoris. So this will be it for the evening. It's not even going to be a carpe noctem view. I can't even show you something interesting. Okay, let me tell you about this galaxy. It'll be on our list for next time. NGC 2274, galaxy in Gemini, the twins, magnitude 12.1, purely face-on, 2.4 by 2.4 arc minutes. It is an elliptical, so presumably it's an elliptical 0. As far to the left on the Hubble de Vauquelaire's morphological chart as possible, and it would be a -8 from Z, which is a lenticular galaxy. This galaxy is 231 million light years distance at plus 33.5 degrees, right ascension 647 and 17. It'll make an excellent study for determining deltas in terms of blue-violet, visual, the J, H, and K bands, because elliptical galaxies are primarily composed, as far as I can tell, of red dwarfs, stars that will live for potentially trillions of years. Their luminosity is mostly in the red band approaching the J. So it does put out some J band light, which I believe is somewhere, trying to remember, 1800 nanometer wavelength. I'll have to, don't quote me on that. We are not seeing anything other than seeing artifacts on the screen, of course, at this point. Hey, we have a double artifact right there. Anyway, so this is our Carpe Noctem view However, the data associated with this will be very interesting in terms of evaluating, as I said, for deltas. So I am going to sign off. I do not expect the sky to improve. It looks like it's pretty blanketed up there. Carpe Noctem.